mu S lambda of x, and in this case, lambda will be some partition of some number. So we can just read these off, okay, which is great. All right, great. So now that we know how to find characters, what do we do with them? So in a paper by Alon Regev, Amitai Regev, Silberger, they investigated various identities inside of the character table of the symmetric group. So I decided to extend this program to this more general family that I was discussing earlier, these Wreath products. Okay. So I'll talk about the Wreath products, tell you what those are. All right, so definition. So let G be a group. Our convention is it's finite. Then the Wreath product G, and then just sort of like this, whatever, one of these signs, Sn. So this is just equal to, you take n copies of G, and you take the semi-direct product with Sn, where the action of Sn is simply to permute the n tuples of G, of Gn. Okay. Another way to see this is you can take the permutation matrices, n by n permutation matrices, and instead of ones in each spot, you put elements of G in there. This is a nice way to see it. Simple representation. Okay, so these are the types that I was looking at. What's nice about these guys is that you know the representation theory of the Wreath product if you know the representation theory of G. There is a very direct method to determining these things. You can look it up in, let's say, McDonald's book is great. It has everything.
So the order of the Wreath product is order of G raised to factorial A?
Yes, right. So it's the order of G, yeah, raised to, and times n factorial.
And can you take the Wreath product of any two groups?
You can.
Yeah,
you can. Okay. But this is what we're interested in. Great. All right, so we want to deal with these. Specifically, I dealt mainly with the Wreath products of this type. So I mainly looked at so Z mod K Wreath with Sn. The reason is the representation theory of Z mod n is a cyclic group. Right? It's determined by a root of unity, kth root of unity. So I know the representation theory of this thing. It's not exotic. You know, that's one reason. Yeah. And you want to start with something small, but I'd also be probably later on be interested in looking at more complicated G's and seeing how that works. Okay. Mainly looked at this one, especially with k equals 2. This is the smallest one. And the representations are very easy to handle. The characters are simple. Okay, great. So first let me say, for these particular Wreath products, we know what the conjugacy classes look like. Okay. So the conjugacy classes of CK Wreath with Sn are indexed by K multi-partitions. So these are K tuples, lambda 1, lambda 2. I'll put them in the top because on the bottom they correspond to the components terms. Where lambda I is the partition of ni, and the sum of the ni is equal to n. Okay? So if you drew all of their boxes, there would be n of them. In the case of k equals 2, you have something like, for k equals 2, you have something like, this. This is what I drew last time, and maybe you'll have a longer one here. So it'll just be tuples like this. All right, great. Now, there's another reason to study the case where k equals 2. And the reason is, maybe I'll call this an example. So when k equals 2, this group already has a name, and it's of interest to everyone. It pops up in Lie theory all over the place. This is the so-called hyperoctahedral group.
Isn't this the group? It's the group of the cube, the n-dimensional cube, right?
Yes. Yeah, isometries. So this is the hyperoctahedral group. It's generated by reflections. It's a Coxeter group of type BCN. It's a wild group of the odd special orthogonal groups, SOS, of the R and so on. So this is another reason. In fact, this was the original motivation. After the symmetric group, this is the second most important. Okay. Very good. So this is a reason. Now, for the hyperoctahedral group, we also have an analogous formula similar to what we have up there for the characters. And I'll just write it down. I'll try not to explain it too much. So to find the characters explicitly, we can again use, let's call this alpha, symmetric functions. I'll define what these things are in a moment. And so this is going to be the sum of, bipartition, and these are the regular Shor functions, x. And we're going to need two sets of variables, x's and y's. So here this would be x and y. And then here I and u would be some bipartition of n. I'll tell you what these are. P plus minus of r of xy is just the old PR of x plus minus the old PR of y. And y, the variables are x1 through xn and y1 through y. Okay. And the action of the symmetric group is sort of whatever you do to the x's, you also do to the y's. And then p lambda of plus or minus xy is just